remind me to start that. Okay, so 1 liter on the bottom, 1,000 milliliters on the top. So if you're starting with us online and you missed the first part because we forgot to turn it on, go to 5th period. And hopefully I've started at the right place there. Okay, liters cancel out. We times through across and we get 18,000 milliliters. Right? Okay, to convert milliliters to grams, basically the same kind of conversion, except it's 1 gram is equal to 1,000 milligrams. I'm going to start with what I'm given again, 450 milligrams, and you always start with what you're given in the upper left-hand corner of your T-square, or your factor label, or dimensional analysis. Whatever I have here is going to be unit-wise down here. Whatever I want to get to is going to be on top. So the 1,000 this time is going to be on the bottom because it's attached to the unit that I want to get rid of. The 1 gram is going to go on top because that is what I want to go to. The unit that I cancel out is milligram. And this time I'm going to divide. So if I'm going across 450, I times it by the 1 and I divide it by the 1,000. So here, whoops, I forgot to trade back out. Here we're going to end up with 0.450 grams. Now when you write a small number like that, I want you to get used to putting the 0 before the decimal. Okay? Everybody okay so far? Chicken and rice. Okay, right here we got 1 liter equals 1,000 milliliters. We start with what we're given, 400 milliliters. And we want to get rid of milliliters. It's going to go on the bottom. Attached to that is the 1,000. 1 liter on the top. Milliliters go out. And I end up with 0.4 zeros. Those zeros aren't there, just 0.4 liters. Okay, see what you can do with D. Yes. I want you to do the think. I know, that's why a lot of you are going to be frustrated for a minute, but I want you to get used to setting up the dimensional analysis. I'm going to be giving you a point for that in quizzes. We have, 1,000 grams is equal to 1 kilogram. So 73 grams, 1,000 grams, 1 kilogram. Grams go out, 0.073. Did I do that right? And then the unit would be kilograms. Now, I know I told you it's going to be frustrating for those that you can do this in your head and you just want to do it. Remember I told you, I know you know how to do this, but this is to show you how to do this dimensional analysis. It will be stuff that you cannot do in your head coming up. Okay? All right, so let's deal with something a little bit more funky here, and I forgot to put these in the back. So I will pass these out down the row. Take one and pass it on. Whoa, hello, heavy on the fingers. You get your own periodic table. And these, I would suggest that you go around the outside of with tape. Do not tape the center, because we're going to be doing stuff with it. Just the outside with tape, because if you don't, by the end of the year, they become so ragged, then falling apart, that they don't stay together very well. Okay? So what I would do if I were you is this is how I fold it. I fold it so I can still put it in my 3-ring binder. So I fold it like that. So I can still open it up, it'll still go in my 3-ring binder, and it'll still fit. And I put this in the front of my 3-ring binder because we're going to be using this a lot all year long. And yes, I print it big on purpose because I like my periodic tables big. I know some others like it small. I like it big so I can put it out and really see it. What? Already colored? You get to color it again. You'll get them again. Okay, so on the back of that, this is why I passed it out right now, is on the back there is conversion factors. And we're going to be using that conversion factor right now. So, calculate the number of milliliters in 4.5 cups. So what's the conversion factor I need? Cups to milliliters. So 1 cup is 236 milliliters. Everybody agree that? Did everybody find that? You see it under volume? Okay, so now we're going to start with our 4.5 cups. And we're going to go, I want to get rid of cups, it goes on the bottom. And I want to get to milliliters, so it goes on the top. And I'm going to cancel it out. I would times through a top, yes. You can shorthand cups, so C. Okay, so when I'm going from a metric recipe to a non-metric recipe, this is what I would need to do. Okay, so if I have a European recipe, it's usually in milliliters. What do I get? Now, if you don't have a calculator, there's some in the sink here you can borrow. If you do have a calculator, get it out because we're going to be using it a lot. Come get them. Yeah, come get them. Just make sure you put them back. As long as everybody puts one back, because I know how many's here, we're good. How many need them back there? And I'll just bring a bunch. You can borrow them while you're in class. You just can't borrow them out of class. Anybody else back here need one? You need one? You need one? You got one? Okay. Oh, you need one? I thought I saw another hand over here. Sorry. Okay. Okay, so let's times that through. Now, I'm going to give you my rules for significant figures. That's probably farther in the notes, but I'm going to give them to you right now. There are 4 of them, and they're very easy. Okay, I don't use the fancy words that they use in your book and that stuff. I use Mrs. Howe's scientific rules, significant figure rules. Number 1, numbers 1 through 9 are always significant, wherever they are. Number 2, if a 0 is sandwiched between 2 numbers that are significant, it's significant. Number 3, if a 0 tells me how well something's measured, it's significant. The 4th rule is a not significant. A 0 is not significant if it just tells me how big or how small. Okay, so those are Mrs. Howe's 4 significant rules. Again, one more time. 1 through 9 significant. Sandwich zeros are significant. If a 0 tells me how well I measured, significant. If a 0 just tells me how big or how small, not significant. Okay, so here we have 2 significant figures times by 3 significant figures. When I'm timesing or dividing, I always take the smallest amount of significant figures to report. So I would report 2. So what do I get for my answer? Give me the calculator throw up. 1,062. So I would put 1,100 milliliters and be done. Okay? All right, so what conversion do we need for F? Miles to kilometers, and we need kilometers to meters. Well, I know that one real quick, whoops, because that one's real fast. One is 1,000. But what's the miles to kilometers? 1 to 1.67 kilometers. Just one what? 09. Okay. All right. So we start with what we're given, 6.7 miles. So we're going to do a couple conversions here. First one, we're going to get rid of miles, so 1 mile on the bottom, and 1.609 kilometers on the top. Miles then go out. Next conversion, we're going to use this one. So we want 1 kilometer on the bottom and 1.60, whoops, try it again, 1,000 meters on the top. Kilometers cancel. Okay, so this one I have 2 significant figures. How many significant figures here? 4. This one is an exact, so I don't count it. Okay, it's exact. So we're going to report 2. So times it through, you got calculator. 11,000 again. Oh no, 11,000. These 2 are really close. That's why I was like, what? Is that what you guys got? Okay, awesome. Okay, we're going to go a little bit farther now. Calculate the speed of a moving truck. Get from 87 miles per second to miles per hour. See if he's speeding. If the speed limit is 65 miles per hour. Okay, so 87. So what conversions am I going to need? Meters to miles. Meters to kilometers. Kilometers to miles. And seconds to hour. Okay, so 1,001 kilometers we had up here. So it is 1.609 to 1. And seconds, 60 seconds equals 1 hour, right? Those are the ones I need. Start with what I have. So this time, 87 meters. The seconds are actually going to go on the bottom because it's divided by seconds. Does that make sense? Okay, so I'm taking one at a time. We're going to have to sort of go like this. I wanted seconds first, get it out of the way. So there are 60 seconds, 1 hour. Oh, there's 360 seconds. Okay, do you want to do it in more than 1 or do you want to do it in 1? Okay, so we're going to have, is it 3,600 or 3,600? 30. Okay, help me zeros. 0, 0, second, right? Thank you. I've got a little bit of a head cold and it's winning. Okay, so seconds go out. Now I'm going to take my meters and take it to miles. But first I got to take it to kilometers. So 1,000 meters, 1 kilometer. Meters go out. And then 1.609 kilometers to 1 mile. Kilometers go out. Now this is where it gets a little tricky. When I put it in my calculator, I need to do it with order of operations. I want to times through the top. Once I've times through the top, I want to hit my divide sign and times through the bottom. If you have a TI, a new one, you can just go 87 times this, divide by this, divide by this. And it should work with order of operations. But to be safe, and especially if you don't have a real fancy one, you need to do it with the parentheses. So how are we doing? Got an answer? Is he speeding? Miles per hour? Is he speeding? What have we got for an answer? Come on, be brave. 87 times 3,600 divided by parentheses. Okay, we got a 3.2 out here. Let's see if I'm putting down an answer. Anybody else got an answer? You got the same one as you.
I did it wrong. That's what I was saying.
Okay, what do you got? What did you get? 194.7. Did I get that? I got 190. Do I have a different answer? I'm going to throw this through because you guys are getting all kinds of weird answers and I don't believe it. Huh? You get that?
You know, maybe if I put the 36,000 in there and
You stuck with a 60, huh? Okay, I did get 190, so you're good.
I put this on the board and I corrected on the side measurements and then I forgot to put it.
Okay, 190 is right. So did we understand how we do that? You just answered your own question, or are you still? Okay, we are going from miles per second, or meters per second, to miles per hour. So the first thing that we did was set it up so we could change the seconds into hours. Okay, then we had the right thing on the bottom, per hour. Now we're working with getting the meters to miles. So the first conversion is to get meters out of meters to kilometers, because that's where we have a conversion between metric and English. So either 1,000 meters and 1 kilometer. At that point, I had kilometers. Then I use the next conversion, kilometers to miles, to get it into miles on top. So my units here, miles and hour, miles per hour is what I wanted. I got 194. Sig figs. So I only had 2 that I could report. So because I only had 2, I still wanted it to be as big as 194. So I had to replace the 4 with a 0. If it had been a 6, I would have rounded up and it would have been 200, and then I'd have to put it in scientific notation to show 2 sig figs by going 2.0 times 10 to the second. Yeah, it's basically you're rounding it. I can't say that it's more accurate than what I actually measured. Does that make sense? So I measured 87 meters per second. I can't say that it's equal to something more than 2 significant figures. Okay? Okay, let's do some more. Actually, let's do some derived units. This is going to be very important to you, this box, in our lab next time. Okay? So if you know these formulas already, great, wonderful. I couldn't remember the cylinder. I had to look up the cylinder, and I couldn't remember the sphere volume, so I had to look that up. So, yeah. So there's another way to do it. But do you want to be able to find a radius, or do you want to just be able to use the diameter that you measure in lab? It's a lot easier to just use the diameter I measure in lab. You can divide diameter divided by 2, too. But you now have a formula that you don't have to do that. It's up to you. Okay, so this is a derived unit in your lab. This belongs in your analysis area. Okay, so data is pure. Data is what I actually measure in lab. That's actually what I observe, which would be qualitative. If I observe something in lab, it's qualitative. If I actually grab numbers in lab, it's quantitative. Those go in data. It's often better to write my data in lab in a table of some sort. Organize it somehow so you know where it came from. A lot of the things I saw coming in with the shaving cream lab were just observations, but they weren't tied to any part of the procedure, so I had no idea what you were trying to say. Okay, so when you did the shaving cream lab, there was on number 3 there was an observation. On number 6 there was observation. On number 7 there was an observation. So if you had said observation for step 3, that would have made sense, you know. So try and tie them together in there. So anytime I do area or volume calculations, I should put it into my analysis part. Anytime I do any calculations, anytime I draw any graphs, that's all in analysis. Okay? Okay, so here we have some examples of what we needed on the other. A circular petri dish with vertical sides has a radius of 7.5 centimeters. You want to fill the dish with a liquid medium to 2.5 centimeters. What volume in milliliters would be required? What about liters? Okay, so what do I do? Do you want to do that? So if I'm finding volume, is centimeter going to end up cubed? Look at the formula for cylinder on your other page. Look at the formula for cylinder. So is it going to end up cubed? R squared H. R squared H. So centimeters squared times centimeter is going to be a centimeter cubed, right? Okay, so give me that formula again. What was it? Okay, so that E squared. Okay, so plug in what we have. So we have a radius, so what are we going to do to get, what else can we do? If we put a radius times the radius by 2, so we're going to go pi 2 times 7.50. Should probably do it like that, not like that, but that's okay. And that's centimeters times height, 2.5 centimeters, divided by 4. What's my volume? Thank you. 225. Anybody else get that?
225.
Oh.
Are we not solving it?
Solve it all the way. You got what? 441? Anybody else get this? Yeah? Okay. So we had 2 significant figures, 3 significant figures. I can only report 2. So what is my answer? 440 centimeters cubed, which equals 440 milliliters. Now, we can go ahead and move it if you want to. What would it be in liters? Because it asks for it both. You'd move it 3, so it'd be 0.44 liters, and I would drop that last 0 because it's just a placeholder. Are we okay? Am I losing you? Where are we going?
So I don't quite completely understand what the sig figs. So there are 3 sig figs, 7.5.
Right, there's 3 there,
So
and there's only 2 in the 2.5. So because that, I can only report 2.
okay.
So I have to take the lowest amount.
You can only be as precise as
Right, right. I can only be as accurate as my least accurate. Okay? All right, let's do this next one. I have 700 or 7500 microliters. Let's try this again. They are very, very little. Of milk needed to be consumed one day. Could it be done easily, with lots of effort, or not much effort at all? Well, should we change it into liters? If you want to. Okay, so in 1 liter, there's 10 to the 6th microliters. Ten to the 6th. Micro is 10 to the 6th. We jump. We don't have anything at 4 or 5. Okay, so what are we going to end up with? 1, 2, 3, 4, 5, 6, 0.07 liters. Okay, so this is a 2 liter. A 1 liter is what pop usually comes in. A tenth of that would be easily consumed in one day. Yeah. Okay, easily. All right, so we now move to temperature scales. We still report here on the weather station in Fahrenheit. Most of the world does it in Celsius. Celsius is a lot easier because you know at 100 water boils, at 0 it freezes, and somewhere in between, like around 20, is nice room temperature. It's easy to go back and forth. Negative 273 is what absolute 0. We've never quite reached it. We've come really close. Difference between Celsius and Kelvin is what we call an absolute scale. There are no negatives, and nobody's ever reached 0 Kelvin. Become really close, but we've never been there. So when we're doing calculations with temperature, and temperature's on the bottom, we don't want a 0, because then we are undefined. And negative sort of messes up everything. So we want an absolute scale. There are, my brain just left, calculations to go back and forth between Celsius and Kelvin, and I don't have them on my brain right now. Celsius to Kelvin, Kelvin is equal to Celsius plus 273.15, and I don't know that it has the other one, the 9/5 one. It's a 1.8. On your thing, it has the example or whatever it is. Okay, what is it? So Fahrenheit equals Celsius. So this one is minus 32 Fahrenheit, and you divide it by 1.8 equals Celsius. I was going to look it up in the book, but... Okay, so if we have a temperature of 77 degrees Fahrenheit, what would the same temperature be in Celsius and Kelvin? So we're just going to throw it into the example here and make it work. So to get Celsius, we would go 77 minus 32 divided by 1.8. Get an answer. What do we got? So 77 is a good room temperature, a little hot for me. I like it around 72. So what would it be in Celsius? 25 degrees. So I told you that I like it around 20 degrees. I like it cool. Okay, so now how do we get to Kelvin? Which gives us 298. And this, when you do Kelvin, it is just capital K. It is not degree K, it's just capital K. Okay? Let's see. Borrow yours just for a second. I want to see how far. Okay, we're almost there. Okay, now we go to the next is a joule. I don't think I've got anything. Maybe I've got. Oh, I just made a bigger picture down there. Okay. I was going, what did I do there? Okay, a derived unit. So that's something that, again, would be in your analysis, would be a joule. A joule is a kilogram meter squared per second squared. And I didn't write that very big. So kilogram times meter squared divided by second squared. Okay, that's what a joule is. It is energy. Yes, these are all derived units of energy. So most of you know what a calorie is, right? A calorie is how much energy it takes, right, to make it through, basically. Well, this is actually, when you see it with a capital C, that's actually equal to 1,000 lab calories. So when you're that's a nutritional calorie. We call it a nutritional calorie. A nutritional calorie is 1,000 lab calories. 1 lab calorie is equal to 4.184 joules. Joules is a metric unit for energy. Okay? It is our metabolic or biological chemical energy. So, and I see most of you didn't. Did I tell you last time to pick up the number? First one here. Pick up your book. Next time, the number with a little person on it, the first person here, grab the book. Okay? On table 1.3 on page 18 or at the back of your periodic table has the conversions, and you should be able to go back and forth with those. And I believe, I'm not going to do more examples because we need to get on with lab. So we're going to stop right there. So put a little star, help me remember where we're at. Okay, lab today is a basic, straightforward lab. There are basically 3 areas. Okay, so we're going to divide up into 3 rows, basically. You're going to do it, let's do this one again in our groups of 4, and we'll just have you slide up and be part of this group of 4 right here. Is that all right? Okay, so 1, 2, 3, 4, 5, 6, 7. That'll work. So there are 3 areas. There's the liquid area over here that you as a group, if it's your turn to have these, you can either come as a group and go 1 through each of these and just read them and agree on what you're reading. Remember to read between the lines. So if I'm looking at a meniscus that goes like this, and I have a line here and here, and this was 21, and this is 22, I'm going to report 21.5 milliliters. It could be 21.4 or 21.5. It's your guess. The last number on a significant figure is your best guess in lab. It's not exact. It's your best guess. Okay? You'll want that bottom layer of that meniscus, so it probably would be a 4. Okay? You can only estimate 1 past what it's measured. Okay, so 1 past its measured. So if the lines are a certain thing, then I can only go 1 place past that for estimation. Okay, does that make sense? Okay, up here in this area, you've got 3 different kinds of rulers, metric rulers. You've got a millimeter one, a centimeter one, and a meter one with no marks. And it tells you exactly what you're supposed to be measuring. So we're going to have a couple of you groups do that. Then this area right here, you're going to have a scale. The scale is a little hard to open, but once you get it open, you just tap it and it will come on. If it's not zeroed out, you just tap it again and it will zero out. If you have things that are going to move around, you put this on it and it'll hold it on top. You put the tare and it'll take it down so it's a 0 again. Does that make sense? Okay, when you're done, just, come on, I turned it off the other day. I think it's a double click. These are brand new, so I'm still, yep, double click. Huh? Well, I don't want it to throw it at the wall. Okay, so here you're going to be measuring 20 pennies, mass of 20 pennies. Ugh. You're going to be measuring the mass of a ruler and the mass of a stapler. Okay? Now I've got 3 staplers up here. One is really heavy and the other 2 are fairly light. So if one doesn't work, you might try another one. Okay? Everybody understand what's going on? The other lab that I gave you, the chemical physical lab, that's the one we're doing next time. Have it in your lab notebook ready to roll. You don't want to just have a paper back there. You want it in your lab notebook ready to go in the back. And then the other paper I gave you is your tabs finally. I finally copied your tabs for you. Okay, the only one that I forgot to change hazard sign to disclosure, so you're just going to have to write it or type it on another piece of paper and tape it on. Okay, so area 1, area 2, area 3. Area 1, area 2, area 3. Area 1, area 2, area 3, area 1. Go. One, two, you're 3, so you're here. Okay, as soon as you get done with that area, you're going to rotate. So 3 will go to 1, 1 will go to 2, 2 will go to 3. Till you're all the way through them. So you can go as fast as you want, as long as there's material. I don't know that we'll have time for computers today, but we will as soon as we're done. Yes. Oh, let me stop this.